Okay. So when you have P and Q as a constants, then first thing what you will do is you will rewrite the characteristic polynomial associated with this differential equation. So characteristic polynomial will be in this situation lambda square plus P lambda plus Q, because note here that P and Q are constants. Okay, so once you have a characteristic polynomial, you will write down the roots of this characteristic polynomial. So you will end up in three situations. One of them, say your roots are real and distinct, or you can have roots to be real and equal, or you can have complex roots. So let's see through an example how we will deal with each of the situation. We have to find the fundamental set associated to each of them. So in this situation, our fundamental set will be e to the power lambda 1x, lambda 2x, where lambda 1 and lambda 2 are roots. In this situation, it will be x times e to the power lambda x, and I will illustrate this very soon. And then complex roots, you will have e to the power ax cosine bx and e to the power ax sine bx, provided your roots look like a plus minus ib. So these will be three scenarios. Now let's see through an example how to deal the problems in each of the cases. Okay, so find the general solution of a homogeneous differential equation. Say this. Now here we have second order differential equation. 11 is a constant, y prime plus 30 times y is equals to 0. Y is an unknown function here. So y is an unknown function and we are looking for y. So first of all, we will write down the characteristic polynomial for this. So characteristic polynomial will be, so what do you think? What will be the characteristic polynomial?
Lambda squared minus 11 lambda plus 30.
That's right. Lambda square minus 11 lambda plus 30 will be the characteristic polynomial. So then we'll find the roots of it. So lambda turns out to be
6 and 5.
right. So you have here 6 and 5 with the factors of the 30, and then negative 6x and negative 5x will make it negative 11x. So 6 and 5, everybody agrees, will be the roots of this polynomial. Question? No? Okay. So once you have a distinct roots, real and distinct roots, then you will write down the fundamental set. So fundamental set will be e to the power 6x and e to the power 5x.
Not C1, C2.
We are just writing
Okay.
fundamental set. And when we say something is a set, like either use set builder notation, curly braces, put the function, or just pick the notation of a set. So this is, these two members will be forming the set. So general solution for this problem will be C1, linear combination of members of the fundamental set. 6x plus C2 e to the power 5x. And since the problem was asking general solution, so we will leave the answer right here. This y. This is your y, unknown function. So pretty straightforward. If coefficients are constant, there is straight away you just find the roots and get the general solution. So is this example clear to everyone? Okay, let's move on to the next one. Okay, so let's see the next example. Find the general solution for the homogeneous differential equation y double prime minus y prime minus 2y is equals to 0. So again, let's write down the characteristic polynomial. So characteristic polynomial will be lambda square minus lambda minus 2. Roots will be
2 negative 2.
negative 2 and 1. So this is also distinct. So will be the linear combination of both of them. Okay, now let's see the other cases. What will happen in this problem? We have a third order differential equation, but coefficients are still constant. It's not necessary that it has to be a second order. If it's a third order homogeneous with constant coefficient, still you can use the same approach. So we will write down the characteristic polynomial and that would be lambda cube plus 81 lambda. That's right, lambda cube plus 81 lambda, because you have y prime, not just y. Okay, then roots of this we pull a lambda out, lambda square plus 81 is equals to 0. This will imply lambda is 0 and another root will be plus minus 9i. Because we have complex, right? Lambda square will be negative 81, and then if lambda square is negative 81, then lambda has to be plus minus 9i. So now you have a complex, you have a real combination of roots. So what is the real part of this complex root?
0.
0 is a real part, that's right. So my a in this setting is 0 and my b is 9. So if a is 0, b is 9, then our solution fundamental set for this problem will contain now 3 members. And it should contain 3 members because it's a third order differential equation. For fourth order, it will contain 4 members. And so on. And we can, if you want, you can check these members are linearly independent by taking a Wronskian. But here, by this, if you get always distinct roots, then e to the power lambda 1x and lambda 2x will always be, the Wronskian of them will always be non-zero. So you don't have to check. But just first time maybe you would like to see what's going on with the Wronskian. So here it will be e to the power 0 times x, e to the power ax, which is 0 times x, cosine 9x, and another member will be e to the power 0x sine 9x. So the reason I am putting 0 because I want to tell you that if there is a real part, you will place it right here. So your fundamental set will be 1, and this will be cosine 9x and this will be sine 9x. Now general solution of this problem will be linear combination of members of a fundamental set. So it will be C1 times 1 is just C1, C2 times cosine 9x plus C3 times sine 9x. So that will be the yx which you are looking for.
So the sine and cosine for the fundamental set of complex solution, that they're not in the exponent, they're multiplied by e?
They are multiplied by e to the power real part of x.
Okay.
We did this in the Euler's identity last time.
Does it matter in what order you arrange your terms from the fundamental set in your general solution? Like, because they can get paired up with C1 or C2.
Right, so good question. Good question. Doesn't matter. You can put the constants in any order. It's just a general solution. But if you apply initial condition, so suppose, say Chase is getting C2 to be 9, and you have placed a C1 in front of the function, and you would be getting C1 as 9. It's just the names of the constants is different, but eventually the solution turns out to be unique. So that's a good question. Okay, yes.
Is it possible for the constants of integration for the two parts of the imaginary one to be different? Like, could C2 and C3 be different, or do they have to be the same in this case?
They have to be different.
Okay.
And you have to place 3 different constants.
Okay.
C1, C2, C3. But then once you find using initial condition, they turn out to be unique. And it does not matter if you name this as C2 or this as C3. Did I answer your question?
Yeah.
I think what you are thinking is you're thinking putting C1 and C1 here, right?
No, I'm thinking putting
No?
C2 and C2. I thought this cosine 9x and the sine 9x would have the same constant.
No. No. Then it would be like one constant dependent second order differential equation, and then why would you need 2 initial condition?
Yeah.
So you should have 2 linearly independent function. So no, you should have different constants for cosine and sine, because these functions are linearly independent and they are giving you the solution of actually y double prime plus 81y equals to 0. So if you try to write down the solution of y double prime plus 81y equals to 0, then that will be just this much portion. It will not involve C1. You see what I'm saying?
Yeah.
So if your differential equation on the top is not y triple prime plus 81y prime, but it is y double prime plus 81y equals to 0, then your polynomial will be just lambda square plus 81, right? And your roots will be then plus minus 9i, that's it. So then in that case, your fundamental set will only involve these 2 functions. And this C2 times cosine 9x and C3 times sine 9x will be giving you a solution. Okay, let's now plug in initial condition, because we do have y at 0, 3, y prime at 0, 72, y double prime at 0, 243. So you have to plug it and get your constants. So y at 0 is 3. So that means C1 plus C2 is 3, because this will go away. Then y prime at 0 is how much? 72. So the derivative of this will involve sine, so that will not contribute. This will involve cosine 9 times C3. I just put it there. Wanted to see if anybody will tell. We have to do y prime. Y prime C1 is a constant, so it's go away. And cosine derivative will be giving sine, so it would not go away, because sine will be 0, sine 0, 0, so this is gone, this is gone. This differentiation will give cosine, 9 times cosine, and then 9 times C3 will only contribute toward y prime. So C3 turns out to be straightforward. What's C3? It's just 8. Now to get C1 and C2, we need another condition so that we can able to get C1 and C2. So let's see what's a double derivative. This is gone. Cosine gives sine and sine further gives cosine, so that will only contribute, because this will give cosine and then further sine, and sine of 0 will be 0. So this is the only term will be contributing, and that's here. How much will be the coefficient? Negative 81. Because first differentiation 9, second one 81 with the negative sign. And you will have cosine, so this is surviving just this much, and this is equals to 243. Right, negative 3. So negative 3 is C2, so C1 turns out to be then 3 minus C2, which is equals to, you have a negative become positive, so 6. So your C1, C2, C3 you already have. Now you plug back in your general solution to get a unique solution. So you get 6 plus C2 has a negative sign. So this is negative 3 cosine 9x, and then you have 8 sine 9x. Now in exam, when you are asked to solve these type of problems and you get the answer, and if you have time, plug it back in the differential equation and check whether your answer is correct or not. You can check your answer. If you plug back this function in the differential equation and it satisfies your y triple prime plus 81y prime equals to 0, then your answer is right. So it's in the case when you have time later on. Okay, so now let's move on to the next example. So this is the answer. Find the solution of initial value problem y double prime plus 8y prime plus 16y equals to 0. Now here the roots will be equal, right? Here the roots are equal, and what are those? Negative 4, negative 4. So this is perfect square of lambda plus 4 whole square. So lambda equals to negative 4 is a repeated root. So one thing we are sure, that for this problem e to the power negative 4x will satisfy it. That part we are sure. Now if you believe me with my that fundamental set x times e to the power minus 4x will also be a member, then you can just go ahead and write down the solution and you are done. But let's see, can we prove it in this problem, that x e to the power negative 4x will also be a solution of this problem. Okay, so now you are not required to show this proof in exam. If you are given a problem like this, you can go ahead and use a fundamental set. But just for understanding purpose, right now I will illustrate why we get x times e to the power negative 4x as second member. Is it clear to everyone? Got it? Okay, so let's see. So one thing you know now, this will be satisfying it. Will satisfy this y double prime plus 8y prime plus 16y equals to 0. This is going to satisfy this differential equation, this function. So one member of fundamental set is there. How to get second one? Okay. So we will make use of Wronskian to prove that. So if we have two members of a fundamental set, what is the definition of Wronskian? So Wronskian of, or maybe first let me write down, let y1x, y2x forms a fundamental set for this particular differential equation. Okay, so let this forms a fundamental set. So we already know one of the members. So say y1 is equals to e to the power negative 4x. And we are looking for y2. What exactly y2 will be? So what is the Wronskian of y1 and y2 by definition? y2 prime minus y2 y1 prime. So Wronskian of y1 y2 will be determinant of y1 y2 y1 prime y2 prime, and that's nothing but y1 y2 prime minus y2 y1 prime. Now let me plug this y1 right here. So I will get here then e to the power negative 4x times y2 prime minus y2 e to the power, so negative 4 times, right, because we are differentiating it, so negative 4 times e to the power negative 4x. So far is it clear to everyone? I haven't done anything. Just plug my function y1 in Wronskian definition. That's it. Okay, what is going on at the back of my mind? I'm thinking to reduce the order of this differential equation. I have a second order differential equation for which I already know this is one of the member which will satisfy it, and I'm trying to look for another one. So if I reduce the order, I will get first order differential equation from second order. And we know how to solve first order linear differential equation. How to solve first order linear differential equation? Integrating factor. Then we'll use integrating factor to solve that differential equation. And that's how we end up getting this second member y2. So that's a big picture. Okay. Now in the process of reducing the order, I will make use of two things. One, definition of Wronskian. Second, form of Wronskian. Now this is an interesting observation which was there in your slides, that if you are given a differential equation, form of a Wronskian is c e to the power integral negative of the coefficients fraction. Let's go back for a moment and let me show you that particular form which is in the slides. So I'm pausing this. So what is this result telling us? If we have a differential equation second order, right, then, and we do not know the fundamental set of this problem. Now you can note here it can, the coefficient can be constants, can be functions of x for this observation. Then we can still find the form of a Wronskian even though we don't know the solutions. And form is given by constant times e to the power integral of a1, which is a coefficient of y prime term, divided by the coefficient of y double prime term dt. So suppose in exam I ask you how to find the, give me the form of a Wronskian. and I give you a differential equation which you cannot even solve. So you will make use of coefficients of that differential equation and will give me the Wronskian, the form of Wronskian. Okay, so now let's use this result. So how will I use this result? Going back up here, I have a constant e to the power negative. What is my coefficient in this differential equation of y prime? 8, and coefficient here is 1, so I will just place 8 in this integral, and since my independent variable is x, I will place it x. So my form of a Wronskian turns out to be in the c e to the power negative 8x. Now, we know the form of a Wronskian. We know by definition what Wronskian will look like. They have to be equal, so we will equate them. And what are we getting when we are equating them? So I will equate this expression which I have here with c e to the power minus 8x. This is by definition, and c e to the power minus 8x, the form of Wronskian. Now this differential equation, let's little bit clean it up. So we have here y prime, and this is plus 4 times y2, and e to the power negative 4x I am dividing, so this is c e to the power negative 8x, and so you get c e to the power negative 4x. So you get a first order differential equation which you can solve. How will you solve this first order differential equation? Integrating factor, because it's not separable. So let's do what's the integrating factor. IF here is e to the power 4x. If I multiply in this equation, I will end up getting integrating factor times y2 function derivative should turn out to be c e to the power minus 4x times e to the power 4x, and this is nothing but c. So I get e to the power 4x y2 prime to be c, integrate both the side, and I haven't yet placed a value of c because I don't know. So let's see now. Y2 e to the power 4x is equals to cx plus some constant of integration. So y2 turns out to be what? C x e to the power negative 4x plus k hat e to the power negative 4x. Now I am saying that let c to be 1 and ignore k hat. Why? Why I am saying that take c to be 1 and ignore k hat. What was the main goal in this problem when we started out with? So let's go back up quickly. So we had this differential equation. We wrote down the characteristic polynomial. We got repeated roots. We picked one of them as satisfying the differential equation, right? So what we wanted the second member of fundamental set. For that, I invoke the idea of Wronskian. So we get by definition this to be Wronskian. By form, we get this to be Wronskian. We equated both of them. And what exactly we are looking then now in this slide? We are looking for, I just want one word, we are looking for y2, second member of fundamental set. That's exactly right. And we end up getting this expression right here for y2. But after I got this expression, I am saying you pick C to be 1 and ignore K hat. Why? Because, yes.
Well, it might be representing C after
We already know e to the power negative 4x is a solution. Any constant times e to the power minus 4x will also be a solution of a homogeneous problem. We are looking for what? We are looking for linearly independent solution of a differential equation. Any constant multiple of e to the power negative 4x will be linearly dependent to e to the power minus 4x. So this is not giving us, this portion is not giving us linearly independent solution. Now this is giving us linearly independent x times e to the power negative 4x. Now since C times this is a solution, any constant will be a solution because it's a homogeneous problem. So you pick one member which is x e to the power negative 4x by taking C to be 1. So your fundamental set turns out to be then e to the power minus 4x and x e to the power negative 4x. This is a proof why the second member of a fundamental set is x times e to the power minus 4x if you have repeated roots. Is it clear? So we did a proof of why the second member looks like x e to the power negative 4x by using Wronskian. We proved it. The second member has to look like this. And once we have them, then general solution is just linear combination. Now your popper is you plug this initial condition which is in this problem and get me the exact solution of this problem. And your initial condition is right up here. And let me paste it on the next page. So you finish this problem by plugging these initial condition in this solution and get me C1 and C2 and get the unique solution.